we'll just start. Okay. Alright, so last time we were talking about these three rules for sentential inference. So you're coming up with a derivation, you're trying to figure out what conclusions you can come to, or what you can infer based off of your premises, and these were our rules. Right?
Right.
Remember these rules?
We may introduce. Yeah.
So I'm just going to re-go over, I think it was the last example we did last time, to reintroduce us to these proofs, right after we introduce conditional premise. Well, maybe we'll go over the rules again one more time to make sure that they all make sense real quick. So rule P is that you can introduce a premise at any point, right? There's nothing wrong with introducing a premise, it's just remember when it's all said and done, make sure you proved what you were supposed to prove. Right? So if it says prove that A logically follows from B, and you prove that A logically follows from B and C, because you introduce C as a premise, it's not that there's anything wrong with your proof, it's that you didn't prove what you were asked to prove. But there's nothing logically invalid about introducing a premise. So you can introduce a premise at any point. Rule T is our tautological implications. So we can introduce another sentence S in a derivation if there are preceding sentences. I'll use S.T. like that all the time for such that. So just get used to that because I do it a lot. So let's restart the sentence. We may introduce a sentence S in a derivation if there are preceding sentences such that their conjunction tautologically implies S. Okay? Now remember, when we say conjunction in this rule, we don't necessarily mean taking two statements, conjoining them, and then what those tautologically imply. It means anding together as many previous sentences as you want. It can be just one, it can be two, it can be three, it can be four, it doesn't matter. Make sense?
I like it.
Because oftentimes you'll just want to rewrite a line, writing it a different way. So for example, we know that A implies B is the same thing as not A or B. So this is tautologically implied by just that. I don't need
not A
multiple
or
ones.
not.
Oh, oops, sorry, thanks. I said it, but I wrote it wrong. Yeah, so this and this are really the exact same thing. So this is tautologically implied by this. Every time this is true, this is obviously true, since they're the exact same thing. So I don't have to take multiple sentences and create a conjunction out of them. I can do it with even just one. So don't be confused by what we mean by the conjunction here. This is a conjunction of any number of previous sentences. It can be one, it can be two, it can be three. It's just typically two. And when we look at our table of common tautologies, we'll notice it's always two, I think. And then rule CP was the weirdest of them. Rule CP for conditional premise is that if we can derive S, some conclusion, from R, some assumption, and a set of premises, so if R and a set of premises implies S, then R implies S can be derived from the premises alone. So here was the truth table that we did for that. So think about P as our premises, R is the if part of some statement we're trying to prove, S is the then part. So what we're trying to prove is going to be something like, show that, given all this information, show that if x equals 2, then x plus 2 equals 4, or something like that. So R would be show that, so P would be a bunch of given information, and they say show that if R, if x equals 2, then x plus 2 equals 4, something like that. And the way that you're going to do that when you're doing your proof is at some point in your proof you're going to assume x equals 2. And show that with all your premise and x equaling 2, we're able to conclude that x plus 2 equals 4.
But how do you show that?
And that's what this truth table is showing. Those are identical. It's the same thing.
So
to show that adding R as a premise implies S, that's the same thing as our premises implying the if-then statement.
Which makes sense, actually.
Is this starting to click from last time, or do we need to write out a hard example?
Right out, it's easy example.
Yeah, we can do our simple example. So we'll do, our premise is just 2 plus 3 equals 5, like we've always been using.
Right.
So now, I want you to prove if x equals 2, then x plus 3 equals 5. So here's what you're supposed to prove, and all you know is that 2 plus 3 equals 5. Ignore everything you know about math. You're now a little kid, and I give you one rule about addition. I say 2 plus 3 equals 5. That's all you know about addition. And now use that little kid when this is all you know about addition. Sorry, using p equals. Let's do p equals that statement.
Computers do this, right?
Use a logical implication?
Yes.
Yeah. Yes.
That's all they do.
A computer, well, the part of a computer that does computing, it's called the ALU, the Arithmetic Logic Unit, and it's just a bunch of logic circuits. So one of the things you do in a computer science degree is you build out of basic logic circuits an ALU, something that knows how to add and that knows how to multiply. And then once you know how to do that, it's easy to create subtraction and it's easy to create division and goes from there. But yeah, it's just using logic circuits, basic logic circuits. So you go from ands and ors and nots to addition, subtraction, multiplication, division, and even jumping conditionals, we'll just say, and conditional statements. Anyways, so here's our only premise. Now we're trying to show if x equals 2, then x plus 3 equals 5.
Right.
So we start out with
2 plus 3 equals 5.
We start out with something like, let x equal 2. Or assume x equals 2.
Right.
Some assumption.
Right.
We add this as a premise. And then we say, then
Since
2, maybe something like then, x plus 3 is equal to 2 plus 3 is equal to 5. Right?
Right.
So we just really showed if it's true that 2 plus 3 equals 5, then it's true that if x equals 2, x plus 3 equals 5. We showed that this being true implies this is true. How did we show that? We assume this is true, we assume this is true, and shows that implies this is true. So in our proof we show this. We show 2 plus 3 equals 5. That statement, and x equals 2, that statement implies x plus 3 equals 5.
Right.
So this is what we show in our proof, and that's logically equivalent to showing that 2 plus 3 equals 5 implies the entire statement
X plus 3.
if x equals 2, or we'll just write it as an implication.
Yeah.
X equals 2 implies x plus 3 equals 5.
That's actually so cool.
Make sense?
Yeah.
So we start out with assuming this and this, show that implies this. And if this is true, then this is true, because they're the exact same thing. P and R implies S is the exact same thing as P implies R implies S.
Because every word is true, the other is true.
And this is how basic theorems that you've used all the time, every mathematical theorem is this type of thing, an if-then. So what's a common theorem that you know?
The Archimedean property.
Pythagorean theorem.
The Pythagorean theorem. So how does the Pythagorean theorem start out with? Starts out with something along the lines, if a triangle is a right triangle, then the sum of the squares of the legs is equal to the sum of the square of the hypotenuse. Right? Does that make sense what I'm saying?
Yes.
So we don't assume from there on out that every triangle is a right triangle. That's not the premise. That's not something that we assume is true. We just know that if it's a right triangle, then the sum of the square of the legs is equal to the sum of the square of the hypotenuse. We don't know that x equals 2 forever on from here on out. This isn't a new premise.
Right.
It's just if x equals 2, then x plus 3 equals 5. Good? Okay, so that was conditional, and we'll do another proof that has conditional premises again to see it. But here was the truth table for it. Where P is our premises, R is our antecedent to the thing we're trying to prove, and S is our conclusion to the thing we're trying to prove. So let's go through the actual example. Leah, you want to just read that to me? So I don't have to keep looking back.
If
Sample
you can't
two.
drive.
Yeah.
If the Cards are third, then if the Dodgers are second, the Braves will be fourth.
We did this example already.
Yeah, I said I'm going to restart with the last example we did.
Either the Giants will not be first, or the Cards will be third.
So say that again.
Either the Giants will not be first, or the Cards will be third.
Okay.
And in fact, the Dodgers will be second. Therefore, if the Giants are first, then the Braves will be fourth.
Okay. So this is a premise, only depends on itself. This is a premise, only depends on itself. This is a premise, only depends on itself.
Now we're going to put in our if G applies.
So we're trying to show that if G is true, then B is true. We're trying to show that this implication is tautologically implied by our premises. So big picture, what we're showing is that this is a tautology. I'm going to write it all out real big once and then we'll be done with it. Trying to show that C implies D implies B and not G or C and D implies G implies B. We're showing that this thing right here is a tautology.
Okay.
So there's one way that we can do it is we can make a big massive truth table. We can plug in every possible combination for C, D, and B and see that this one is always true. The column for this thing.
It's only 8 rows though.
No, G as well.
Oh yeah, I missed one. Should be 16.
Okay.
C, D, B, and G. So you'd have to do 16 rows, but also how many columns do you need?
Quite a few.
Yeah, you're going to need a few columns, you're going to need a few rows. That's a big table. Chances are you're going to make a mistake somewhere in that table. I bet you would. Especially because you get bored enough that you try just short-circuiting it and make a mistake. The point is, that's a tedious way to do it. But ultimately, we're doing the same thing. We're showing that this is a tautology. This is always true. That's what we're proving. We're just not going to do it with the truth tables anymore because this is too tedious. Everyone understand the problem?
Yeah. Wait, I don't understand it because our implication is our premise.
No.
Or sorry, not our premise, is our conditional premise, right?
We will make G a conditional premise to prove this.
Okay, but that's
You gonna make me
our
write it?
implication is proving it.
Okay, so showing that this is true is identical to showing that this is true.
That's what I needed.
So we're going to go show this, and since this is true, then what I had written before is true.
So
And then we're
if,
done.
okay.
But this is not our endpoint.
So we're trying to show the Braves are
Our
there.
endpoint is this.
So we're trying to show that if Giants are first and Braves are first.
We're trying to show that given all this information, if G then B is always true. If this is always true, then this.
It seems like that's
get
what
rid of
we're
all.
trying to prove.
If this is true, then this is true.
It seems
is what
like
we're proving.
what we're trying to prove is that B is true.
No, we're trying to prove that if G is true, B is true. Same thing as over here. We are never trying to show that x equals 2.
Right.
We're trying to show that if x equals 2,
Right.
x plus 3 equals 5.
So then we say if Giants then.
Because we don't want G to be a premise. We don't want x equals 2 to be a premise. We don't want our system of mathematics that we're developing to have to rely on the fact that x equals 2 is universally true.
Right.
So we don't want that as a premise. Make sense?
Yeah.
Okay, so that's what we're doing. Let's erase that and let's show it. Okay,
So for
yeah, so for,
G implies B.
no, we're going to introduce
B is
G
true.
as a conditional, that's supposed to be C, as a conditional premise.
G is true?
conditional premise.
It's a conditional premise. Let x equal 2. Let
so
g.
now our statement is going to say, if G implies B and G is true.
So now we're going to work our way down to B. So we're going to show, assume G is true. That means B is true. Therefore, all this implies that if G is true, B is true.
Oh! Okay.
This is what we're trying to prove.
Yes. So we're doing our first assumption right now.
Yeah, that was our conditional premise.
She crying.
No, she's just sitting up. We shut that door, so much noise doesn't go that way. Okay, so now we introduce 4 as a conditional premise. So 5. Now, if we know that G is true,
Not G or
and
C.
we know that it's not G or C, we now know that C is true, right?
Right. 'cause
And this is dependent on,
2 and
well, this is tautologically implied by 4 and what?
2.
2. And this now depends on premises 2 and 4.
Yes.
Right? So 6, since we know C is true, we know D implies B. Right?
Oh yeah, because anything true. No, that's not true. Anything
From C and C implies something. Here, I'll write one side. If I know A and I know that A implies B, I know B.
Okay.
This and this tautologically implies this.
Then why don't we know B right now? In our implication.
Well, you can see that already, but I've got to use one step at a time.
No.
Since I know that C is true, I know that what C implies is true.
What I'm saying is, since we know that G is true, why don't we know B?
How would we know B?
Because it's just barely right there. Look, since you know A is true,
Tell me what premise you're referencing up here.
4.
Premise 4 is just G.
Right. Okay, yeah.
This isn't a premise. I can't use this to prove it.
I know, that's what seems stupid to me. I was like, okay, look, we just use it to prove it.
No, that's what I'm trying to prove. So I'm using this rule.
Yes.
If you know A and you know A implies B, you know B. So I know C, and I know C implies this, therefore I know this. Right? So this is tautologically implied
And you know D.
by 5 and 1. And so now we're using premises 1, 2, and 4. Right?
Yeah.
7. Now from 3 and 6, I can conclude B.
Right.
So B is tautologically implied by 6 and 3. Now I'm using premises 1, 2, 3, 4.
6. 1, 2, 3. Are you using 6 as well?
These are the lines I'm using. These are the premises I'm using.
Oh, right. Yeah. Okay, yes.
So I'm using all the premises that were on line 6 and all the premises that were on line 3.
Right.
Okay? And then so from 8,
Wait, you're not using 4 though? Oh, because you used it up there. Yeah, I never.
yeah, I'm using 4 because I use line 6. Line 6 uses line 5. Line 5 uses line 4.
Right.
So I am using 4.
Right.
Okay. So then we can conclude B. So finally, we can conclude G implies B. G implies B. And then I can't remember how he says it. Oh, where it started and ended. So that is 4 and 7. Why is he writing the rule after?
We already decided that's that weird.
So using conditional probability for 4 and 7. And now we only depend on premises 1, 2, and 3. So this implication, so these 3 premises tautologically imply this.
Okay, explain that because you're using line 4.
No, I'm not. I'm no longer using the fact that G is true.
Yeah, you are.
No, I'm not. Same thing as when I do this. I assume x equals 2. So that leads to x plus or equals 5. So now I know if x equals 2, x plus or equals 5. I'm no longer using the fact that x equals 2 to say this statement's true.
I'm not wrapping my head around the fact that
Assume-
you're able to drop 4.
Because I'm no longer assuming G is true.
I thought that's the whole point.
And
If we assume G is true, then we know B is true.
So what did I prove now? Now I proved that my premises imply if G is true, then B is true. That's what this sentence says.
Right.
I showed that if G is true, then B is true. I do not know that G is true. I do not know that B is true. I know that if G is true, then B is true. I assumed G was true, and show that led to B being true. Now I'm no longer assuming that. From here on out my proof, if I had to continue with my proof, and maybe I was proving some other thing and this was just a side proof, I can no longer use the fact that G is true. I could only use the fact that G implies B is true.
I'm not satisfied with that.
It's like proving by contradiction.
I understand I understand the whole idea. I am confused with how you're able to use the fact that G was true
Okay.
to only negate the fact that G was true.
Let's look over here. If I show that P and R implies S, right?
Yeah.
Here's my premises, here's my conclusion.
Yeah.
Over here, my premises are only P, and my conclusion is an implication.
Right.
These are identical. I can go from this to this.
Yeah.
That's what I'm doing. I got rid of the G and put it over here. So now it's not premise anymore.
That makes more sense.
Okay, that's the way to explain it. Okay. And that's the proof. That's what we were after. Any questions about anything there? Anything weird? Anything need more explanation? You good? So you ready to just reproduce it? I'll read you the paragraph and you just prove it.
Yeah.
Yeah.
Oh, Jacob, I should probably give you fair warning.
Am I in this book?
No.
Dang.
You might be trying to tag you as a math teacher this year.
You?
I'm gonna learn so much.
Huh?
I'm gonna learn so much.
It's your class though.
We lost 3 math teachers, and so we need teachers to teach the lower level classes.
Like Trig?
Lose.
We lost Teresa, John Colley, and Dina.
What happened to Teresa and John?
I don't know. I just know that they're not teaching this year.
Isn't Teresa
Whatever,
the
our
that
class
just
is
came
even
back?
better.
Teresa's gonna have a date, that might be why.
She taught for 1 year.
Well, she's been in and out.
I know, I'm just saying. 1 year is not a long streak.
Needs
I
more
know.
teacher, huh?
She didn't even do her streak when she taught Nazar. She just there for a
So
year.
this
and
would
not.
be, is Trig a higher up or is that, would this be geometry?
Algebra two.
Masada does geometry. Big air quotes, because no they don't.
Yeah.
And so now the academy is responsible for Algebra 2. So I don't know if there's still a geometry course. You might know better than me.
I teach algebra too.
There's a
I
lower
would
geometry
love
course
to
if you
teach
didn't
algebra.
pass
I
it.
don't need,
If
I
you
don't
didn't-
need the credit,
if-
and I don't need the math
If
class.
you didn't pass it in 9th grade,
Algebra
you have to
2
redo geometry.
was-
So we do
Lydia-
carry,
Dina was
Lydia
teaching.
does,
Well, Trig was
I
higher
think
than
it
that.
needs Lydia.
so we do carry the notion of people didn't pass geometry. So we're gonna have to have a geometry class, an algebra 2 class, and a college algebra class. Are the ones that we need filled.
Why do you need it?
College
You don't
algebra?
necessarily need a college algebra class.
College
For the
algebra.
lower
Well,
class?
We did that for the kids, not necessarily because it was needed.
Well, even if you do what the academy calls trig, which is not trig, it's pre-calc. That is a hybrid of college algebra and
Yeah, college, what we did was basically, in college algebra, what Teresa said was basically pre-calc minus the trig.
right. So we do a college algebra no matter what. It's just a matter of if it's a hybrid with trig or not.
Never do
The
it.
academy always offers college algebra. We can't not.
I would not.
It's just we offer pre-calc, which includes college algebra, or we do just college algebra.
Okay,
But we always do college algebra.
why?
It's the next thing you take.
Are you gonna
That's what you do after algebra 2.
jump
College
on
algebra.
yes if you report to you?
You
Oh,
basically,
yeah.
what,
Oh, yeah.
why are they, What I didn't understand,
Maybe
I
I'll.
realize
yes,
you've
sorry.
learned so
I'll
much.
going through algebra
Sometimes.
2 and then college algebra, there
I'll
were
be awful.
absolutely no
Because
difference.
I'll think in my head and I don't verbalize it.
Because
Well,
So you see?
the way that the textbooks are designed is every algebra textbook is this material. Your algebra 1 textbook is this material. Your algebra 2 textbook is this material, and your college algebra textbook is this material.
Yeah,
And so you'll notice half those textbooks aren't needed.
what, it's not half the textbook, like, the units are
I could
almost
do. I
exactly
could
the
teach a
same.
student pre-algebra, and then algebra 2, and then the second half of college algebra, and cover all the material.
I'm just saying, the second half of college algebra was the same as the second half of algebra 2.
It shouldn't have been. There should have been new things. You should have been learning how to calculate like determinants.
We did that. Okay, so there were like 2 lessons that were in. I didn't know determinants, but as far as units went, the units were the exact same topics.
Sometimes what the difference is they introduce a unit to you, an idea to you, and only give you really simplified examples.
So it just gets harder. It's basically hard algebra 2.
Right, so maybe you did come across a determinant in algebra 2, but it was only for a 2x2 matrix, so you just have to know this times this minus this times this, and that's it. And never had to really have a concept in your head of what the matrix is really representing, what the determinant really is.
Yeah, we didn't
Stuff like
do
that. Well, yeah, like I say, I hate the way they do it all together. There should just be an intermediate algebra, college algebra. That's it.
Not algebra 1 and 2.
No pre-algebra, no algebra 1, no algebra 2, no college algebra, how they do it. I have 2 textbooks, intermediate algebra, college algebra. I could cover those 2 textbooks with the student, and they'd be far better off than those 4 textbooks are going to do in that I have to go through. Regardless.
And it's half the time.
Maybe. Just because it's less textbooks doesn't necessarily mean it's half the time.
Yeah.
Well, it doesn't take.
But it should be
It
less.
shouldn't take 4 years to teach that issue.
Right, it should take 4 years, and it could potentially take 2 years, but they're more difficult in that they require more from the student.
Yeah. Yeah.
Anyways,
Have the teachers met? Is that why you're telling me this or what?
Sophia was texting me, and she seemed like she was a little worried, so I was thrown out, I guess.
But so if you,
I would love to do that,
that's
and
a problem.
that'd be easy to do on this.
Sophia only teaches 1 though, doesn't she? She only teaches trig. No,
She
she
has
teaches
to drop
geometry
other
too.
commitments.
Probably.
Sophia?
Like Edson.
Yeah.
Sophia, yeah, I'm not sure how many classes Sophia is doing, but I thought she was
Oh, and
doing
then
3.
nightly commitments, so you
I
won't
think
get
last year
the
she only did 2.
Yeah.
She did just a trig
I'll have to
course
read
for
chapter
sure.
before class every time.
Oh, I think that she was
Prepare a lesson.
supposed to be supervising a TA doing something
You'll help do it.
for one of
Just get out of
the
here, guys.
algebra courses.
I
I don't know if it was Lydia.
Lydia, probably.
Like Lydia was the one in the classroom, but
Where do
Sophia
you guys
was
go
supposed to
into
be
next year?
overseeing what she was doing.
What does that even mean?
You don't think to trig next year?
So Sophia would be
Yes.
responsible for things like developing a syllabus,
But that's what your class is in, trig.
Yeah.
Sophia would
Can't let
probably
you do
teach
that.
you.
making sure that course material is covered, picking the course
I
material.
got trig from Don. That was more fun.
Hmm.
That was a fun class.
Yeah, I wouldn't want to do what
I'd
Lydia's
love to
doing.
teach trig.
I would never teach where someone told me
However,
what book
if
I
I
had
had
to
to,
use or
I'd
what
have to
material
do
I had to cover.
I'd be good at that.
But it is a part of the process that is a hard part of the process. Like one of the longest things is trying to find a book that's good.
Trig is
We find
complicated.
the
I
same
still
thing.
won't teach trig
No.
because I don't have a good textbook for it.
Have you looked at like a bunch of them?
I've tentatively looked at a bunch of them. I've only really looked at 2, I think. But haven't found one yet.
Sounds right one, I guess.
I mean, same thing when I was looking for a geometry book before I taught geometry. I found that textbook last minute. When I started my geometry course last summer, I couldn't find anything, so I started out with Euclid's Elements.
Which is way better.
I went right back to Euclid because I couldn't find a good geometry book.
You didn't think of grandma?
Before Christ.
I didn't. So that's not a book I ever used.
I didn't like
But you did geometry?
I found it in another way. Looking to get copies of it, found out how rare it was. And then in just talking with someone about it, they said, I think that's the book Masada uses. And I went to the library and I had a bunch of copies. So I lucked into finding out about that, but no, I had no clue about that
Really?
textbook, and I had no clue how good it was.
That's
That textbook is great.
Because like even before you ever went through it, I had known about it. Just I guess because my siblings had known about it for years.
Yeah, so that's the one that advanced students would go through.
That's what
Or
everyone
behind
went through.
students.
Or behind
Right.
students.
Oh,
Yeah.
behind students?
No, I'm saying, well, brother colleague taught.
Did he do some behind students?
Yeah.
Wow. He really did that.
Yeah. One class, 1 year.
I wonder how that went.
I would be so
I wonder if
scared.
you got frustrated.
Yep. Well,
Just kidding. He doesn't even care about it.
I'll do stories.
Here's all the time. And then he leaves.
Alright, let's continue. Let's do another example. You just want to read it to me again? Oops.
This one's about horse races then.
Yeah.
Okay, if A wins, then either B or C will place. If B places, then A will not win.
If B places,
Then
then
A will not win.
A will not win.
Yeah. If D places, then C will not. So D then C. Therefore, if A wins, D will not place.
A implies not D, is what we're trying to prove, right?
Yeah.
Yeah.
Okay. So this is a premise, it just depends on itself.
Okay, my brain's just eating that really fast.
This is a premise, only depends on itself. This is a premise, only depends on itself.
Get it now.
Yes.
So maybe we should have Jake prove it
I'm
instead.
proud of you.
Jake says he wants to do it.
Yeah.
dude.
I heard that. I'll do it.
You might want to. Alright, it's easy. You just.
Come on.
It's true.
I don't know if I'm bad at doing like
Too late, get up there.
A's not true.
Bad at doing all
Anything
this.
to let you sit down.
Conditional.
That means
Okay, well,
Yeah.
we're assuming
premise.
A is true, so
Right.
we're gonna let A here.
So do an indent when you introduce a conditional premise. Try to make it as obvious as you can.
Big A.
So A, and that's now a conditional premise, and it only depends on itself,
Whoops.
which is
Four.
like 4.
This is 4.
Okay?
Why
Yeah.
are you doing 3 lines? Oh,
Because A is true, B is not true. Do I need to rewrite that as the,
No.
you can say
Okay.
No, you can go
A
flat
is
out to
true.
not B, is what you know
B
is
or
true.
C.
And that's tautologically implied.
by 2 and 4?
Mm-hmm.
Why
A is
Just comma,
Oh.
comma 2, comma 4.
Comma 2, comma 4, right.
Tautologically implied by 2 and 4, and now we're using premises 2 and 4.
Right.
Good.
Okay. Now that you know B is false, you know C is true.
Not yet. So you need to say B or C is true.
A.
B or C is true, but B is
You need
false,
to
so C
say-
is true.
I know, but you're trying to
Can't
do a
you
lot of
say
leaps in one
because-
go.
Oh,
A is
right.
true.
Right.
Yeah,
Okay.
You know
Yeah, B or C is true because A is true.
there you go.
So you know.
Right.
This is tautologically implied by 4
And 1.
and 1.
Now.
So you're only using premises 4 and 1.
Now you know C is true.
Yep, now you know C is true
Ooh.
because it's tautologically implied by,
5 and 6.
Oh, there you go.
Uh-huh.
yeah.
And now you know that C is true.
And this uses 4 and 1
And
5.
no, those are the premises.
Oh,
you're
these
using.
are all premises. These are
Yeah.
premises. My bad.
So you need to do
One
the
and
union
two.
of all the premises on the previous lines.
Right. So it's
1 and 4 and
So
2.
two.
1, 2, and
Yeah.
4.
but also on the one above you is 2 as well.
Yeah.
No, it's not.
No, it's not because I didn't use 2 that time.
Because
Oh
we
right.
didn't use 5.
Okay, and because C is true,
Then not
D is false.
Mm-hmm.
Right.
So not D. Wow.
Got it.
That's by
We did all this
3
in head well done.
and
Right.
7.
Every bit of it.
And that's all the premises.
Mm-hmm.
And yet you didn't want to get up there and do it.
Me?
Yeah.
And that
Did I want you
basically
to drop dead?
shows what we were trying to show,
Basement?
which is A implies not D.
Right, so that's line 9.
That's 9.
Using
Yeah,
what
only
else
for that,
is-
so everything that was-
And then you do that a condition.
Jordan,
C dot
more than
P.
Everyone drops dead due to engagement.
And
It's not tautological
It's not
implication.
tautological.
So C dot P, and then where you started at 4, where you ended at 8. So C dot P, comma 4, comma 8.
Not Sammy.
Isn't it C dot P, comma
4, where you started.
4?
8, where you
Oh,
finished.
yeah.
Make sense?
Mm-hmm.
And you use the premises 1, 2, 3.
And now you're only
I
using
used
premises 1, 2, 3.
Right.
Now you know.
Yep.
So that implication is a logical implication of those 3 premises.
Just big juicy government
Let's
things.
do another one.
Man, that's fun.
Yeah.
Yeah, I took started it.
Took square root.
Mine's good geometry.
By the way.
How is it?
Yeah.
Geometry.
I was like, I want someone to read that.
See, what are we doing here? Now we're having the conversation of inbound.
We got there.
Okay. So let's have this conversation. So far we've been showing that
I know. I'll tell you later.
giving these premises, you could come to this conclusion.
Yeah.
So now what about if there isn't a way to go from your premise to your conclusion?
What do you mean?
So here's the example. So an invalid argument. To show an argument is invalid, find an interpretation where the premises are true and the desired conclusion is false.
We did not go over all that stuff.
I know, I forgot this, and that's why I put it after all that.
It's interesting because the exercise is really like led up to that.
So notice what we were showing last time. So before, what they were claiming is, if this is true, then this is true, right?
Right.
And we went through and we said, yep, that's valid.
Oh!
You can go from these premise to this conclusion. That's valid. What if there was no way to do this?
Be invalid.
It'd be invalid, but how do we show that? Do we just keep trying forever until...
No, you show
Show
counterexample.
that it's
Yeah.
So here's how you do it. Basically a counterexample. So let's look at a simple one. Let's say our premises are A or K, and K,
It's true.
and we're trying to prove A,
Right, obviously.
okay? Now obviously if you know that A or K is true and you know K is true,
A has
you
to be
don't
false.
know that A is true. No, it could be true or false still,
It's
Yeah.
an or statement.
Oh yeah, this is inclusive or.
right? So the way that you show an argument is invalid is you try to come up with an interpretation where the premises are true and the conclusion is false. So here's a simple example. Let A be the statement 1 plus 1 equals 3, and K be the statement 1 plus 1 equals 2. Notice, is it true that 1 plus 1 equals 3 or 1 plus 1 equals 2?
Yeah.
Yes.
Yes, so this is true. Premise 1 is true.
Right.
Premise 2, is it true that 1 plus 1 equals 2?
Yes.
Yes.
Yes. Conclusion, is it true that 1 plus 1 equals 3?
No.
No. So if you can find an interpretation where your premises are true but your conclusion is false, then the argument is not valid.
But you put random things in like we did, or that was just
You come up with interpretation.
like an actual something.
Well, we're talking about sentential interpretations. You could have just as easily thought in your head, okay, let's make A false, K true,
Right. Right.
then true or false is true is true, but false is not true.
So that
And then
would have
you
been
just
one of
pick sentences.
would that have been one of your conditional premises? Let A be true.
A conditional premise is something you do when you're proving something. We weren't doing a derivation. We were showing that you couldn't derive A from these premises.
Right. And the
Over here, we could derive A implies not B from these premises.
Right.
And one of the ways we did that was with conditional premise. That was a tool we used to show that these do logically imply this.
Right.
And then obviously another way to show that it doesn't logically imply is to just do the truth table. To show that an argument's invalid. Okay. So that's what he's talking about here. It's a pretty simple idea. And now let's move on to some useful tautologies. So he goes through explaining all these tautologies. I think it's better to just go straight to the table and go through all of them.
You want to go through all of them?
Yeah.
Okay.
These are all the useful tautologies. I want to make sure that all of them make sense.
Okay.
I'm not going to wrap truth tables problem.
else how they
Well, I will write them all down to make sure that we're all on the same page. So P and P implies Q implies Q. So are there any questions about how this is a tautology?
Real quick.
If you know P is true, and you know that P implies Q, then you know Q is true. Example, if you know Donnie's wearing his shoes, and you know if he's wearing his shoes, then he's wearing his socks, do you know he's wearing his socks?
Yes.
Yeah.
That was a good.
Okay, so that's the first one of these tautologies. Next one, we have not Q, maybe I'll leave these here since we're going to be doing it over and over again. Not Q and P implies Q implies
Not P.
not P.
So exactly the same thing. Oh,
Donnie's
negative.
not wearing socks.
Well,
If you know,
that makes sense.
if Donnie's wearing shoes, then Donnie's wearing socks, and you know Donnie's not wearing socks,
It's
It's
not
not
wearing
wearing
then I'm not wearing shoes. Good?
Yeah.
Another way to think about this P implies Q is it's contrapositive. So P implies Q is the same thing as not Q implies not P.
Right.
And so if you were to rewrite it that way, if you had not Q and not Q implies not P, then you know not P. And you'll notice that this is exactly what the other one said, right? It
Right.
said P and P implies Q implies Q.
Right.
Okay. So there's that tautology. Let's do the next one. Not P and P or Q. So if you know not P and you know P or Q,
Yeah, that makes
then you know Q.
Right.
So if you know Donnie's wearing a blue shirt or Donnie's wearing a red shirt, and he's not wearing a blue shirt,
He's wearing red.
then he's wearing a red shirt.
Obviously.
If you know that P or Q is true, and you know that P is false, so if P is false, P or Q is true, Q has to be true.
Problem is you're wearing a blue shirt.
Wow, should I have said that different? Didn't really think about it. Sorry if that's confusing.
The next one's probably the opposite.
Okay, so everyone's good with that one?
P and Q implies.
Should probably be going over the names of these as we do it.
Law of
exportation.
Law of detachment, modus tollendo tollens, modus tollendo ponens. Ponens? Those were the three we just did. Now let's do law of simplification. If you know P and P implies Q, right?
P and Q implies P.
Oh,
P and
oh, it's way simplified, so we don't need all this structure. So, if you know P and Q, then you know P is true.
Also know Q is true.
For snap.
If P and Q are true, do you know P is true?
Yes.
Yeah. And yeah, we didn't do the P and Q over there because we already know X implies X. Oh, which is the next one. Why would they put that in an and? So obviously this is true and obviously this is true. P and Q implies P and Q. You remember going over our precedents? And always takes precedence.
Yeah.
Yep.
So that's what it looks like with the parentheses. So obviously something implies itself. I don't understand why there's a special case one with an and. But there is. Yeah, it doesn't make sense if you try and put parentheses in unexpected places, so. Alright, that's it. Okay. Law of hypothetical syllogism. Okay. So if you know that P implies Q,
It's a syllogism.
and Q implies R, then you know P implies R.
Wow.
Yeah.
That
Big.
That's just a
Transitive
property
property.
right there. Transitive. Is that
We just did the reflexive property, now we're doing the transitive property.
P implies Q and Q implies R and P implies R.
P implies Q and Q implies R implies Q implies R.
That makes sense.
Right. If P is true, Q is true. And if Q is true, R is true. Then if P is true, R is true. Okay. So, yeah, there's hypothetical syllogism.
What is got gas?
It's got gas. There you go. So if the car is moving, it's got gas.
Alright. Oh, this is the one we just did.
Simple sentences bring us joy.
P and Q implies R is the same thing as P implies Q implies R. So this is exactly what we said over here.
Yeah.
It's how we get rid of one of our premises.
P and yes.
That would make sense?
Yeah.
Yeah.
The one right here. It's one we've been using for our conditional premise.
What's that one called?
Law of exportation. And next we'll learn how to import.
Previous one.
Oh, import's just flipping it around because these are logically equivalent. So import is this.
So,
Why are they called that?
I don't know.
how come they don't use
I don't know
it if
how-
only in-
Most of these get their name.
Oh, it's right there.
Law of absurdity, I know how that one gets its name. That's because that's what you use in a reductio ad absurdum argument.
Oh, that one.
So that one is P implies Q and not Q, or contradiction. That implies not P.
Okay, that doesn't make sense.
That makes.
And
So here's the way to think about
it has to be false.
This is always false.
Right.
Yep.
Make sense?
P
Q
implies
and not
false.
Q is always false. So, if P is true, then something false is true. So P is false. If P is true, then Q and not Q is true. That's impossible. Q and not Q, this is impossible.
Right.
So how do you read the sentence? You read the sentence, if P, then Q and not Q.
Yeah, that doesn't make
So you can't have P, so you have not P.
sense. Okay.
Make sense?
Yes.
Wait, isn't that always true though?
So really, when you're like doing a proof.
Oh, that's always false.
No, it's always true.
Because Q and
Yeah,
not
The
Q
whole
Q and not
statement
Q
is true.
can.
Right,
The
I'm saying-
implication, this is a tautology, maybe we're losing
I
track
know,
of what
I
we're
know, I know. I'm talking about just the Q area.
And should we do it all in one go?
Why not?
We'll do P implies Q and not Q, right here. And then we'll do,
Not Q. Not
no, P implies Q and not Q implies not P. So let's just do it. Alright, so our combinations are true, false, true, false. Okay, so notice this part's always false.
Right.
So true implies false is
False.
False.
true implies false is false, false implies anything is true, false implies anything is true. Good?
Mm-hmm.
Okay, so now we're doing this implies not this.
Right.
So false implies false is
False.
true.
True.
False implies anything
Oh,
is
yeah.
true. False implies true is
True.
False.
No, it's true.
Oh,
It's
sorry.
false implies false.
false implies false
It's
is
true.
true. Thank you. True implies true is,
True.
and true implies true is.
True.
So it is always true. This implication is always true. It's a tautology. So if you know this, then you know this. That's a simpler way than how I wrote it out. When I go over reductio ad absurdum, I should have read these things. Oh well, you'll see it two ways. You sound like Harry Potter spells. Alright,
I'm not going to character.
so we're done with the law of absurdity, the law of addition. Hopefully this will make sense.
So
P implies P or Q. If you know P's true, you know P or Q's true.
yes.
Right.
So you can or on as many statements as you want. You didn't change the truth value of it. Good?
No P's true, you know.
Then you know P or Q's true. Yeah, one of them's got to be true. One of them's true.
Wow.
Okay. So let's see.
Law of double negation.
So those were tautological implications. Now we're going to go over tautological equivalences.
P is the same thing as not P, obviously.
So P is logically equivalent to not
Perfect example.
not P.
Summarize.
In other words, not false is true. Well, that's not in other words. Not false is false, and not true is true. Is what I meant to say.
Not false is true. Gosh.
Everyone good with this?
Yeah.
Nothing weird? Alright. So that's the law of double negation. The contrapositive. So P implies Q. This is one that we use a ton. Is logically equivalent to not Q implies not P.
We just barely used that one. That's the problem.
So if there's fire, then there's oxygen. Is logically equivalent to if there's no oxygen, then there's no fire. Thank you. You made me take a bow. De Morgan's. This is another great one.
These are the ones that I struggle with. Remember.
So not P or Q is logically equivalent to not P and not Q.
Or
Similarly, not P and Q
Or
is tautologically equivalent to not P or not Q.
you.
You did it backwards for there, but
Not
not
P
the
edge Q. So equivalent to not P or not Q.
So if not
How does that make sense?
and
So let's look at the first one.
not or.
So
Yeah, makes sense.
first one, P is Johnny's holding a marker, Q is Johnny's holding an eraser.
Okay.
If I say, I'm not holding a marker or an eraser, I'm not holding a marker or an eraser, what does that mean? It means I'm not holding a marker and I'm not holding an
That
eraser.
makes sense. The other one hurts me.
I'm not holding a marker or an eraser,
Oh, it's the same
I'm
thing.
not holding a marker, and I'm not holding an eraser.
Right.
Or.
You know I'm not holding a marker or an eraser. You know I'm not holding a marker. and I'm not holding an eraser.
You gotta listen for the animals.
This is subtle.
Yes.
I don't know why you guys are laughing. Did I say something wrong?
No.
No, it just sounded like you said the same thing
It
twice.
barely clipped.
Oh, okay. Alright. Do we need to go over it one more time, or is this perfect now? Everyone understands
That's
it?
good.
Okay, so let's do the next one. If I say, okay, you don't know, see what I'm holding,
Okay.
but I give you a hint. I say, I'm not holding a marker and an eraser.
Okay.
What are the possibilities?
You're holding one of them.
You're
I'm holding
none of
one or neither.
Or not, right.
But for sure, either I'm not holding the marker or I'm not holding the eraser.
Ah.
Right.
Good?
Yeah.
If I'm not holding both, then I'm not holding one or I'm not holding the other.
Right.
Okay.
Do we need to come up with different sentences to make it click again, a different way?
Yes.
You do too.
Fishes in the sea.
Okay. P is car 1's in the parking lot, Q is car 2's in the parking lot. I say car 1 and car 2 are not in the parking lot. It's not true that both of them are in the parking lot. So you know either one's not in the parking lot, or the other's not in the parking lot, or both aren't in the parking lot. I don't know.
Makes perfect sense.
Yeah.
Maybe
So
try going it
confusing when
from the other way. Let's say it this way. I say, I'm not holding a marker, or I'm not holding an eraser. What do you know for sure?
You're not
You know for sure I'm not holding both.
Right.
So maybe going from this to this is easier way to think about it. Good?
No, good.
Alright. Morgans. But basically, when you distribute the negative, you flip ors to ands and ands to ors.
Morgs.
De Morgans.
Morgan.
Yes. And we'll also probably get to the law and set theory, I assume. On the road.
The communicative law.
Commutative law.
Got him.
So we already know this. P and Q is the exact same thing as Q and P. Same thing if I switch those to ors. Right? Order doesn't matter with ands and ors.
Didn't we go over that? Oh, we did it with an amplification.
So that was the commutative law of equivalences for implication and disjunction. Oh, yeah, we already went over this.
P.
So, P implies Q is the exact same thing as not P or Q. And so if I know not this implication, I think is what they're doing, right? Yeah, they're not in the implication. If I not the implication, then that's the exact same thing as knotting this, right? Which is the exact same thing as using De Morgan's P and not Q.
Okay, will you please explain this, the intuitive sense for this one here?
Sorry, one sec.
Getting your brain damage?
Just had a sharp headache. Wait for it to let go. Okay. Sorry, what?
Explain this one, please. P implies Q is the same thing as not P or Q.
This is the same one we went over last time.
No, it's not.
Alright. So let's say if I'm wearing shoes, then I'm wearing socks. Then you know one of two things. You know either I'm not wearing shoes or I'm wearing socks. If I'm wearing shoes, then I'm wearing socks. You know either I'm not wearing shoes or I'm wearing socks.
Right.
Yeah.
Good?
And just so happens when you're wearing socks, you're wearing shoes. That doesn't matter.
Maybe. I could be wearing socks without shoes. That's still possible.
Alright.
Either I'm not wearing shoes or I'm wearing socks. If I'm wearing shoes and I'm wearing socks, it's the same thing. What do you know? Either I'm not wearing shoes or I'm wearing socks.
If I'm wearing shoes, then I'm wearing socks. If I'm not wearing shoes,
Or in
and I'm not wearing shoes, or
You know one of two things is true. Either I'm not wearing shoes or I'm wearing socks. One of those is for sure true.
It is the same as the last one.
it's not.
It's the
Okay,
same.
let's go over.
It's not.
Let's say that I am wearing shoes. Which of these is true?
Q.
Q. Let's say I'm not wearing shoes. Which of these is true?
No, P.
Not wearing shoes, yeah. So you know one of these is true.
Alright.
Good? And then I don't have intuition for this.
Right, but
See, basically the same thing.
Yeah, well, yeah. So I don't know how to do the intuition in one go from this to this.
I'm not wearing shoes and I'm not wearing socks.
I don't know how to say. If it's not true that when I'm wearing shoes, then I'm wearing socks, you know I'm wearing shoes and I'm not wearing socks.
You just said it.
Right, I don't know how to make the intuitive leap. Those sentences are too complicated for me to know how to make an intuitive leap with those. But the derivation is really simple. Okay, so good with those? Okay. What did we just do? So now we're on law of negation for implication. Oh, we just did that. Oh, well, I thought those were all combined with that. Oops. So yeah, those were two separate ones. Thought that was a lot combined. Okay. So now, a law for biconditional sentences. We already know that, but we'll write it out. P implies Q and Q implies P is logically equivalent to. P is logically equivalent to Q.
That's not what I
There's
said.
got parentheses around P.
Oh, I see. I look at the bottom.
Yeah, you do. Right? That is how they should have done it. Lost it.
Okay.
Oh, they just did it the other way.
What's the point of doing it the other way?
Well, they just did this to this. But it's a double arrow, so it doesn't matter.
Yeah.
Yeah. And then finally, another law for biconditional sentences. P implies Q is logically equivalent to P and Q, or not P and not Q.
That's weird. Oh no, that does make sense.
So let's see.
Because either they're both
If you know
Or
P
not false,
and
false.
Q, or not P and
S.
or
and.
And
Is logically equivalent to P is logically equivalent to Q. Done. So what do we mean when P is logically equivalent to Q?
basically the same.
We mean either they're both true or they're both false.
Right.
Right.
But we mean either they're both true or they're both false.
Yep.
They have the same truth value. Well, yeah. Right. All right, and then two more tautologies. P or not P is a tautology, and then not P and not P is a tautology. P and not P is always false. Not false is always true.
Yep.
And P or P is always true. Or P or not P is always true. The sky's blue or the sky's not blue is always true.
the answer's 6 or the answer's not.
Right. The answer's 6 or the answer's not 6. Good? That whole table makes sense? Okay, this is going to be a reference table that you use from here on out when you're doing your proofs. So we've been writing tautologically implies. Now you write the rule next to it that you're using,
Nice, we didn't fill out all these things.
so that you know what rule you're using. So that it is nigh into impossible for another human being who has taken logic before to look at your proof and not be able to reconstruct it.
You can do that.
I should be able to write a computer program to check the validity of your proof. Be able to read what you said the tautology is that you're using, plug in the premises that you said, and see if I get the conclusion that you said you got.
We're going to be using the same tautology, right? I'm just wondering.
But now I just have a table of tautologies.
Okay.
No, I'm kidding. Don't really do that. That's what the author's going to tell you to do in some exercises. Don't waste your time writing down all those rules.
I was actually excited. I was like, I get to learn to say something.
Yeah, if you want to sound smart, learn some Latin names and say it.
Where's our spell?
But I will never,
That'll make you smart.
well, I think you were saying reductio ad absurdum. That's the one that you will most likely for sure get out of this because it's actually one of our rules. So we have these 3 rules. The next rule we're going to add is rule RAA.
Reducto is a spell. Inspired. That's a.
Okay, so there's our table of tautologies, tautological implications, tautological equivalences. He does another example using them, blah, blah, blah. Now we're to exercises. Look through the exercises, see if there's one you're interested in. We didn't talk about exercises to begin with.
We did.
Well, we hardly.
Did anyone do any homework?
I read through them, but I didn't really do them.
You're doing like a weird smile.
Yes.
You for sure did it. Okay. I'm like, is this a halfway? Like I kind of did it.
I didn't do number 7, but I did the rest of them.
Is that because you got stuck on number 7, or because you felt like it was a repeat and you didn't want to do it?
It's because I just didn't do it.
So you just didn't, it's not one that we need to look at?
I don't think so. Well, let me look at that.
Well, if we need to look at it, we can look at it. If any of these exercises look interesting to you guys, we can go over them. Otherwise, we'll continue.
Let's just continue.
You just want to keep going?
I want to go through them before. That's a lot of exercises.
Yeah, but they're just doing what we've been doing. They're giving you a paragraph, and then you construct the proof.
It's
So
not.
there's only 14. It's just they're giving you big paragraphs that you're going to really quickly symbolize.
Number 7 is fine, but it'd be nice to know if they did them right.
So pick
That
one.
makes sense. Pick one.
Yeah, pick one that you think is the most convoluted. We'll go over it.
Out of section 1.
No, out of whatever homework you did. See if I can find the exercises. Jeez. Did I pass the exercises?
It's on page 26,
You guys do that crap.
25, and 26. In the book, not on.
25.
Well,
Okay.
it's predicted to do.
What number?
I haven't chosen one.
Logical,
Either 2 or 3, whichever one you think is harder.
Okay, we'll do 2 since that's where I learned it.
It doesn't go up.
3's probably harder.
Alright,
No,
so
no,
3.
it goes up.
No, it doesn't make sense.
3. Suppose someone proposed as the only rule of inference, from P we may derive Q or not Q. Does this rule violate criterion 1? Does it violate criterion 2? If so, explain why. So does this rule violate criterion 1? You guys remember what criterion 1 and criterion 2 were?
Is it those?
No. So we talked about last time, we had 2 criteria written up here that we need our rules of logical derivation to follow.
Wasn't that where you could attach more onto it? You could and more statements.
No, that's sentential, whatever it's called.
Oh,
Interpretation.
Yeah, you're talking about these rules right here. But when we were creating our rules for sentential derivation, we needed, or for inference, we had 2 criterion that we wanted our rules to follow. So our first rule, our first criteria, or the first of the criteria, was that whatever our rules are, they need to allow us to come to every conclusion that logically follows.
And
Oh,
only
yeah.
conclusions allowed.
Oh, wait, the first one is only the conclusions that logically follow from our premises, and then the second one is every conclusion which logically follows. Okay, so suppose someone proposed as the only rule of inference, from P we may derive Q or not Q. Does that violate our first criterion?
No.
No.
No, there's nothing wrong with P implies a tautology,
Should have been number 2.
right? But does it violate rule number 2?
Yes.
No.
Does it violate criterion 2? Criterion 2.
You can
It
do
says
more with that.
every,
Yes, it does violate criterion 2.
right?
How?
There are lots of things we'll never be able to prove if our only rule is P implies Q or not Q. If that's our only tautological implication, then we couldn't do, almost anything. We couldn't do this. We couldn't show that A and A implies P. With those premises, we would never be able to conclude P.
Hello?
Why?
Because the only tautology we're allowed to use, the only rule of inference we're allowed to use is if I know A, then I know
A or not.
A implies Q or not Q.
Right.
So if I know A, then I know Q or not Q, and that didn't get me anywhere. I already knew Q or not Q. It doesn't add any information.
But
So what do you write?
And that's my only rule. The key word here is only. Suppose that someone proposed as the only rule of inference.
so how does it violate criterion 2?
criterion 2 says our rules of inference need us to be able to include
All.
everything which logically follows. So P being true logically follows from these premises. There is no way for me to use that rule, P implies Q or not Q, and come to this conclusion. So one of our rules is this exact rule. All these tautological implications are valid rules of inference.
So what would you write next?
It violates criterion 2. That's what it says. Suppose someone proposes the only rule of inference from P we may derive Q or not Q. Does this rule violate criterion 1? No. Does it violate criterion 2? Yes. If so, explain why.
You're not able to derive every...
You can't derive new information. Q or not Q is a tautology. We already knew that. P implies true. Anything implies true. We already know is a tautology.
Right.
There's no way for me to derive new information from the information I'm given with that. Like this, for example. There's no way for me to conclude P from these premises using that rule.
Right.
I need other rules. I need to use, well, this rule, since it was basically just a tautology.
Right.
But obviously in our proofs, we've used these tautologies over and over again. If in any of those derivations you told me this was the only rule you can use, there's no way for me to go about doing it. Because there's no way for me to get new information. Okay. So that was a flashback to older ones. So you guys just want to continue? You didn't want to do any of the exercises here?
No, let's do them at home.
Oh,
Sure.
is that what you're going to do?
This humble about.
It's
We're
humble
going
about.
to do the exercises.
Yeah,
Alright.
I like the pictures of them.
Well, if you don't want to do any of the exercises, let's continue. So the next section, the two things that we're interested in is determining if a set of premises are consistent or inconsistent. And then we're also going to introduce the idea of an indirect proof, or a proof by contradiction, or a reductio ad absurdum proof. Okay? Big picture, that's what we're doing. So let's start out with, what does it mean for a set of premises to be consistent?
They don't contradict each other.
They don't contradict each other. This is a common thing anytime you have two kids who had a dispute and you're trying to get to the bottom of it. So kid A says they started it, they hit me first. Kid B says, no, you hit me first. Both those premises can't be true. One's true, one's false. Those are inconsistent premises, right? So one of the ways we think about, are my premises inconsistent, is it impossible for them to all be true? If there's no way for them to all be true, then they're inconsistent. In other words, if I were to draw out a truth table for him, handling all the combinations, if the truth table is always false, then they're inconsistent. Now, if there is an interpretation which makes the premises true, then they're consistent.
And interpretation is your if then.
An interpretation is an interpretation. So if I give you some random things like, so I give you A, I tell you A, I tell you not B, and I tell you A and not B is your premises. Are those consistent?
No.
Yeah.
Yeah, there's nothing wrong with those.
Oh yes.
It's possible for all of them to be true. I can come up with sentences for A and B such that all these are true, right? But if we made it like that, there's no sentences you can come up with A and B that make all three of these true. So these are inconsistent.
Right.
But these were consistent. That doesn't mean if you draw out a truth table that A is always true. It just means that there is values we can assign to A and B such that all these are true. Or there is an interpretation such that these are true. So these are consistent premises. It's perfectly valid for all three of these to be true. That's possible. So these three can be premises. They're consistent. But these are inconsistent. Okay? So one way we can determine if a set of premises is inconsistent is to look at the conjunction of all the premises and decide that it can't be true. Another way that we can determine if a set of premises is inconsistent is if the set of premises implies a contradiction. Notice that if a set of premises, it's a good thing we just did that problem instead. If a set of premises implies a contradiction, that violates rule 1. Rule 1, or criterion 1, sorry, I shouldn't say rule since we use rule for these. Criterion 1 says that our rules of logical inference should only allow us to conclude things which are valid. Right?
Right.
So if I have premises which are all true, and I'm using valid rules of inference, then I can't come to a false conclusion.
Right.
So if my rules are good, and I came to a false conclusion, it's because my premises were bad. You see what I'm saying?
Yeah.
So that's the other way. So if we can take a set of premises and show that leads to a false conclusion, or an absurdity, something that's always false, then we know that the premises are inconsistent. Good? Because sometimes just looking at the premises, it's not obvious right out the door that they're inconsistent. Then you do some work and you see, this leads to contradiction. So they are inconsistent. So best to see by example. Now we have that conversation, so let's put it so we can't see how to do it and make sure we can figure it out on our own. But this is asking for us to show that the premises are inconsistent, right? The purpose of the following example is to illustrate how the rules of logical inference may be used to show that set of premises is inconsistent. Yeah, exactly. So we're going to do this example, and based off the premises, we're going to show that there's a contradiction. Now, we don't know what the contradiction is going to be. We're just going to show that somehow we can get to a contradiction. Make sense? And therefore, all our premises cannot be true. They're inconsistent. All right. Lee, you want to read it to me?
If the contract is valid, then Horatio is liable. If Horatio is liable, he will go bankrupt. If the bank will loan him money, he will not.
Sugar. Let's see what they use as letters. Money. M for money. Okay. Sorry. Were you reading the third sentence?
If the bank will loan him money, he will not go bankrupt. As a matter of fact, the contract is valid and the bank will loan him money.
Okay, let's make sure I symbolize that correct, because they should start out the same way. Do we symbolize it the same way? B implies L, L implies B,
That's an obvious
M
contradiction.
implies not B,
Yeah.
B and M. Yeah, you're going to see that these two lead to B and not B, right? That's what you're seeing. So, go through it. Premise, 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 premise. This only depends on itself. This only depends on itself. Jeez, too big. This only depends on itself. This only depends on itself. Okay. So, 5, what can we conclude? We can conclude L from
V.
From 4, this is tautologically implied by 4 and by, well, maybe we should do this in steps. Let's just say that we know V. This is tautologically implied by 4. And now we're using premise 4. 6.
Wait, you don't know V. Why do you know V?
I know V and M, therefore I know V.
They're both in order.
If V and M are true, V is true.
Oh, that's
It says as a matter of fact.
Oh, right. Okay, this is going to be cake.
Yeah, this was a premise. Sorry, I'm slanting a lot. You with us now? Since I know V, I know L from 5 and 1, right? So I know L, that's tautologically implied by 5 and 1. Now I'm now using premise 1 and 4. 7. If I know L and I know V, that's tautologically implied by 6 and 2. And now we're using premises 1, 2, 4. And then,
If you know M.
8, I'll say I know M. That's tautologically implied by 4, right?
Yeah.
This is only depending on premise 4. 9, I now know not B.
Which is a
This
contradiction.
is tautologically implied by 8 and 3.
Is that your
And that's
contradiction?
not using 3 and 4. No, the contradiction is,
B cannot be.
yeah, it's a conjunction between a statement and its negation. So now I know B and not B. That's tautologically implied by 9 and by 7. And now we're using premises 1, 2, 3, 4. So those premises are not consistent because they implied the contradiction. So they can't all be true.
Okay, take us through the thinking to get B and not B. L and M? I'm confused.
Okay, so here's where we're starting, right?
Right.
I know B and M are true.
Right.
Therefore, I know B is true. Okay? Since I know that B is true, I know that L is true.
Right.
Since I know that L is true, I know that B is true. So now I got B. Now I'm going to get not B. Restart. From B and M, I know M. I know M implies not B, therefore I know not B. Okay, so I now know B and not B. Contradiction.
So you just put it in. Why'd you add? Oh, because you went and added everything to 7. Okay. Okay. I'm with you now.
Good? So yeah, pretty close to exactly what he did. Oh, he skipped the step that we didn't have to do. You see how he went straight to B implies B? So since you know B implies L and L implies B, one of our tautologies was the hypothetical syllogism. So you know B implies B from those two lines. Slightly different proof, but follows the exact same thought process.
He's just using the rules of
He's trying to do singular.
Yeah, he's
Hypothetical
listing out all the ones that he's using. Okay. Let's do another one without seeing those. Okay,
War? Is that war?
let's see. As an application of this method, consider the premise that, so what are we showing here? Once a logical technique for showing that a set of premises is inconsistent has been described, it's natural to ask about the existence of a similar technique for showing that premises are consistent. Okay, so I think now we're going to show that set of premises is consistent
Well, I thought that just
instead of inconsistent. No, we showed that these premises are not consistent because they imply contradiction. So they can't all be true. Now we're going to show that it's possible for this set of premises to be true. Okay? You see the difference in what we're doing? We're going to find an interpretation that makes it true. That makes our premises true. Okay? So let's get rid of this and let's restart. Alright, you want to read it to me?
If war is near, then the army was mobilized.
Sorry, say that again.
If war is near, then the army has mobilized.
Should we do if war, then mobilized or army?
Mobilized.
If the army has mobilized, then labor costs are high.
And high labor.
However, war is not near, and yet labor costs are high.
So not war and labor costs are high.
Yeah,
And L.
yeah.
Okay?
So war
So
implies
the
L,
army
not
is
war,
mobilized.
and L. Should be not war, or L.
Oh,
No, I'm not saying you did it wrong. Sorry, I'm just thinking out loud.
okay. So that makes sense what we got?
Yeah.
Okay. So we need to come up with interpretations where B is false, or where we need a false sentence and a true sentence.
Where this works.
Huh?
We already,
We're showing that these are consistent.
that they are consistent?
Uh-huh.
Yeah, they are. So, they already gave sentences.
Well, now we can come up with. Yeah, they gave us sentences, and then we looked at this, but now we. I guess we'll skip to how he does it to show you what I'm saying. So, see what he does there? So, we pick sentences that are real easy to identify W, A, and L. Okay, we use the same ones. And he says, we'll make this one 2 plus 2 is 5, 1 plus 1 is 2, and 2 plus 2 is 4. So we just need to come up with a false statement, a true statement, and a true statement, and we're good. So that's what he's basically doing. So we just need W to be a false statement. He used 2 plus 2 is 5.
How does 2 plus 2 is 5 imply that 1 plus 1 is 2?
Hold on, let's finish. L, give me a true statement.
1 plus 1 is 2.
And then I need one more true statement.
2 plus 2 is 4.
Okay, so now let's check. Is it true that if 2 plus 2 is 5, 2 plus 2 is 4?
Yeah.
Yeah, that's true. Okay, so this premise is true. Is it true that if 2 plus 2 is 4, 1 plus 1 is 2?
Yeah.
Yeah, that's true. Is it true that 2 plus 2 is 5 is false, and 1 plus 1 is 2 is true?
Yes.
So we came up with an interpretation.
That makes sense.
But the original example doesn't even use a false.
It just went around.
Yeah, it does.
The point is,
Well, it does.
we
The
just
implies
need
went around
any
the end.
sentential interpretation.
Okay, I get that.
So it's like, save yourself the work. Stop thinking about the content of the sentence
And just use the sentence.
and just use
The structure.
the structure of the sentence.
Right.
I mean, a much simpler way to do this would just be, can you assign truth and false values to make everything true? And yeah, we can, because that's what you're really thinking in your head. You say, set this up as true, or sorry, so it's going to be false implies true is always true, true implies true is always true, and not false and true is always true.
Right.
And then we just made up sentences that we need to satisfy that.
How does that prove that your premises are consistent?
Your premises are consistent if there is an interpretation that allows them to be true.
Only so if there's one.
Yes. All you need, if you were to write out the entire truth table for your premises, if there is in your column that is the conjunction of all your premise.
Right.
If there's one T in that column, one place where all your premises are true, then they're consistent.
Right.
Notice what you're doing
Because
with
then every interpretation of that will be true as well.
No, not every interpretation of your premises are true. But when you're doing your proof, all you care about is if your premises are true, then something else is true.
Right.
When your premises are false, you don't really care about it.
Right.
As long as when they're true, the implication still works.
Yeah.
So all you're curious about is it possible for them to be true? Or did you give me premises that don't even work? They're not even consistent.
Well, doesn't that value
Okay. The point.
evaluate
What I'm trying to say is,
criteria too?
What we're
finding
asking
one
is,
interpretation, using instead of that interpretation, how does this prove that those are consistent?
well, notice, if I were to go and do a sentential interpretation where I replaced the sentence, if war is near, with 2 plus 2 equals 5,
Right. So
write it all out and do the same replacements with these, and then symbolize it, I would still symbolize it this way.
So what I was saying before is, if you can find one interpretation, you can find any number of interpretations you want that also make it true.
Correct.
Basically, an infinite amount of interpretations.
Right, because there's an infinite amount of true sentences and false sentences.
Yes.
All that really matters is, can I come up with truth and false values that make all these true? If I can,
Then it works.
then they're consistent, and I can use those as a basis for proving something. If I
I like-
can't, then they're inconsistent, and I'll always be able to prove a contradiction.
This might seem stupid to me.
It's interesting though.
I love the false true. Just say W equals F.
Right, that's
A
why I
equals C.
skipped this, but that's a skip. We're jumping ahead. We'll get to this
Oh,
in chapter 4.
okay.
But remember, what we're still talking about is sentential interpretation. We haven't gotten to interpretation yet, and it keeps making us screw up a little bit when we try to do stuff. Like,
Interpretation versus.
you remember when we tried showing that this was a tautological implication,
Yeah, it was hard.
and then we were thinking, well, wait a second. This isn't true every other sentential interpretation,
Right.
and it's not true under every sentential interpretation. It is true under every interpretation, though.
What's the difference?
So we'll get to what an interpretation is. So we start out with a sentential interpretation, and the way to think about it is, if something's a tautology under every sentential interpretation, then it's also a tautology under every interpretation. So it's a sufficient condition, not necessarily a definition.
Right.
So he's given us sufficient conditions, and we're doing proofs, even though we just have a sufficient condition, don't have a perfect definition yet. And we're going to add to our logic as we go.
So
But
he's
yes,
gonna
we
give
would
us-
eventually think about it this way. Good?
My question is, Donnie, why would you put W as false, as a false statement?
Because I need not W and L to both be true. Look, if I tell you that not W and L is true, if I tell you that this is true, what do you know?
W has to
You
be
know
false.
W is false and L is true.
Yeah,
So W needs to be a false statement.
okay.
So, false. So I made this false, this true, this true.
Mhm.
I just needed this to be translated like this, because now if you evaluate each one of these, they're true, right? False implies true, true. True implies true, true. Not false and true, true. Make sense?
Yeah.
We good? So that's how you show a set of premises is consistent. If there's any sentential interpretation under which the conjunction of all the premises is true, then they're consistent. Okay. Now we're finally going to get, I think, to reductio ad absurdum, or proof by contradiction. So let's continue with my proposition here. So a set of premises is consistent if they cannot, is inconsistent, sorry. A set of premises is inconsistent if they cannot altogether be true. Right? Otherwise they're consistent. If they're not inconsistent, they're consistent. If they're not consistent, then they're inconsistent. Okay, notation from here on out. I may use this fancy P with the loop on top. This stands for the conjunction of all our premises.
Okay.
So it stands for, if I have n premises, it means premise 1, and premise 2, and premise 3, and premise 4, and premise 5, all the way, all the premises. Does that make sense?
You're gonna use that.
This notation might be a little bit weird to you, so for those of you guys who aren't comfortable with that notation, that's fine. Just understand that this, when I do this loopy P, this is a conjunction of all our premises. If I have 3 premises, it's premise 1, and premise 2, and premise 3.
And that's what you're gonna be doing the rest of the ever.
Yeah, from here on out, we're going to use the fancy P to represent the conjunction of all our premises.
What was it used for in our other experiment?
Power set probably as a function. The power set of x is equal to the set of all possible subsets of x. It's capital X where x is a set. So, the power set of the set 1, 2
Right.
is equal to the set containing the set 1, 2, the set 1, the set 2, and the empty set.
Right.
That's common use for it.
Okay, I was just wondering because I remember seeing it in that class. You kind of just have to interpret the context to know when to use it in this specific circumstance.
That's how it is with all symbols.
That's okay, fair enough.
I mean, we did it with all sorts of things, especially in discrete math. There were times where we were using a power 2 to mean
Right,
all the different subsets. I mean,
right.
yeah, we use different notations a lot, or we use the same notation a lot of different ways based off of the context and based off the field of math you're in. Okay, so proof by contradiction. How does it work in general? Oh, now let's finish this. I keep looking at that instead of where we're at. So are we all good with what the fancy P means from here on out?
Yeah.
The conjunction of all the premises. Okay. Okay. So now, something that we already said, but let's say it again. So, when we were trying to show that a set of premise is inconsistent, what did we do? We show that it implied a contradiction. That was one way to do it. Right? So if I can show my set of premise implies something false, then this violates criterion 1. Criterion 1 says from our premise, we should only be able to derive things which logically follow. Right?
Yeah.
You with me on that criterion 1?
Mm-hmm.
So, if our premise can imply something which is obviously false, something that's not true, that's a violation of criterion 1. Criterion 1 is specifically saying we can't allow this type of action. We can't allow our premise to imply something that doesn't logically follow, something that's false, something that's not true. I can't use the rules of math and come up with 1 = 0. Something went wrong. That isn't something that should be allowed from our axioms in math. Right? So our premise implying something false violates criterion 1. So if our premise implies something false, then our premise has to be inconsistent. We have a bad premise. One of them's got to get at least. Right?
Mm-hmm.
Okay. So, and then we went over when a set of premises is consistent. The set of premises is consistent if there exists a sentential interpretation for which P is true. If there's one interpretation that makes the conjunction of all your premises true, we're good. They're consistent. That's what we just did over there. We took those 3 premises that we had, we came up with an interpretation that made all 3 of them true. True and true and true is
True.
so the conjunction of all of them is true. Good? Okay. So now we're ready for reductio ad absurdum. In short, how does this way of thinking work? So, what's a good way to say this?
You assume something's true and you prove that it's not with your other premises.
Right, so I'm wondering, so I have my set of premises, and I'm wondering if the statement S is true, okay? The way I do it is I say, what if statement S was false? If statement S being false leads to something impossible, then S couldn't have been false. There's one way to say it. If I can show that S being false, if I can show a statement being false implies a contradiction, implies something impossible, then S can't be false. Therefore, it has to be true. So if S being false implies something impossible, then S has to be true.
So you show that S cannot be false, so it has to be true.
There you go. If S were false, it leads to an impossible worldview. Therefore, S has to be true. Just like you said.
Impossible world would be P and not P.
P and not P, a contradiction. It would be S implies false being true. An implication of the form S implies false. This being true.
So if that's true, then then something's wrong. Something's funky.
So here's how we say it. So if not S implies false is true, then this can't be true.
Right.
So it has to be false. So if I tell you that this implication is true, then you know that this piece of the implication has to be false, which makes S true.
Right.
Right?
Oh,
we know
right.
that true
Right.
implies false
Right.
is false, right?
Right.
So if I tell you that this is true, then we can't have true implies false. So this has to be a false implies false. And if not S is false, then S is true.
Right.
Yeah.
Okay, so here's how a reductio ad absurdum proof works. Remember, we can introduce a premise at any time. There's nothing wrong with that. So we're going to, it's kind of like a conditional premise, we're going to introduce a premise, not S, show that leads to a contradiction, and therefore S has to be true. If S can't be false, S has to be true.
Right.
Okay? So let's write out a truth table for what we were doing. I did it harder than the way he did it, but maybe it will still make sense. So we're going to write out a truth table. P is a conjunction of all our premises, right?
Okay.
S is the new thing that we're trying to prove. We're trying to figure out if S is true or false. C is a contradiction. So it's always false. C is just some contradiction. You with me on the lettering so far?
Yeah.
All our premise, the new statement, a contradiction. Okay? We're going to show that our premise and not our new statement implies a contradiction
No, our
is the same thing as our premise imply S.
I thought our contradiction is our new.
No. So if I can show that not S implies false, then S has to be true,
Yes.
right?
Yes.
So if I can show that my premises and not S implies a contradiction or something false, then I know that my premises implies S. I'm showing that this and this are the exact same. If this is true, this is true. If this is false, this is false. These are logically equivalent. That's what we're doing in this truth table.
Implies S because and not S. Okay. Yes.
So if our premises together with not S leads to an impossible worldview, then S can't be false. S has to be true. Therefore, with our premises, S has to be true. If our premises were true, S has to be true.
Right.
And that's what we're showing here. So we're saying it up. All our premises can either be true or false. S can either be true or false. Here's all our combinations. True, 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 false, false, true, false, false, right?
Right.
Our contradiction is always false. That's what contradiction is. Whatever the contradiction is, doesn't matter. It's always false.
Right.
If S is true, not S is false. If S is false, not S is true.
Right.
Now we're showing that our premises and not S implies a contradiction is the same thing as our premises implies S. Because remember, as we're doing our derivations, we need to keep track of what premises our conclusion depends on. Right? So notice S is only going to depend on P. It's not going to depend on P and not S.
Right.
It's only going to depend on P.
Right.
So when it's all said and done, so we're going to construct our proof this way, and then we're going to jump to this step and notice that not S is no longer a premise. So we're going to get rid of it, and we're going to be back to the premises we started with.
This is honestly bad.
Well, it's bad something. Not sure of that letter.
It's definitely not
It's
bad
badass.
logic.
It's bad planning.
Okay, so let's make sure that this truth table makes sense.
It's not.
So hopefully we can do this on the fly. So, true and false is
False.
false. False implies false is
True.
true. Alright, let's do it again. True and true is
True.
and true implies false is
False.
false. Alright, next one. False and false is
False.
True.
False.
false and false is
False.
True. False. Yes.
and false implies false is
True.
true. Finally, false and true is
False.
and false implies false is
True.
true. Okay, so that was a messy one. Now let's do this one. This one's straightforward. True implies true is
True.
true implies false is
False.
false implies true is
True.
false implies false is.
True.
And sure enough, they're the exact same thing. They're logically equivalent. So if you have this, you can get rid of not S as a premise, and you go back to your initial set of premises.
That is bad.
And that's what we're doing when we're doing proof by contradiction or reductio ad absurdum. We're showing it's impossible for S to be false, therefore, if our premises are true, S is true. Let me say a slightly different way to be more accurate. If our premises are true and S is false, is it possible? Then, if our premises are true, S is true. Maybe that was more confusing.
No, it's the same
Now,
thing.
we're good?
Yeah.
Okay. And then we already talked about this, that was earlier stuff. So that's all there is to reductio ad absurdum.
Yep, sir.
No. It's actually great logic. Well, shell teams are absurd, logically.
And it's really useful.
Yeah, we use it all the time.
It's
Very
useful to
common
show
proof
things
technique.
are impossible.
Huh?
It's just funny how useful it is to show something's impossible.
Yeah, something leads to contradiction. How useful it is to show it's impossible for something to be in a particular state, or something being in a particular state is impossible. Okay, so let's go over now his outline for how you do these proof by contradictions. He's not using C for contradiction here. He's using C for the new statement that we want to show is true. So fancy P is a conjunction of all his premises, and he's saying you introduce not what you're trying to prove. We were using S over there. The way that we were using S over there, he's using C over here. Okay? So he's saying you have P and not C, have those as premises, and you're eventually going to get P implies C when we're all said and done.
Right.
Okay? So he's using C, how we're using S over there. And then S and not S is just his contradiction. That's the same way that we were using C.
Why did he do that?
I just wrote this proof out. I didn't look at the book while I was doing it. Otherwise, I would have did it how he did it earlier in the tautological table. But this is a perfectly valid way to think about it. Okay, so let's see. So you have your initial set of premises. You introduce not C as a new premise, and you show that P and not C together implies a contradiction. Okay, so therefore, not C implies your contradiction, or in other words, C is true. So if I know it's true that not C implies false, the only way for this implication to be true is if I have false implies false, right?
Right.
Right.
So not C is false.
Right. So C
And
is
if not
true.
C is false, C is true. So this tautologically implies C.
Interesting.
Bad A.
If you know not C implies a contradiction, something that's always false, then you know C is true.
So not anything implies false. Means that thing is true.
Okay.
If you
So
know
many of these little things you
an implication is true, and you know the consequent is false, then you know the antecedent is false.
Yeah.
And not false is true.
Yeah.
Right. We good?
Yeah.
So there's his outline for how you set these up. And then he wants to do one, so let's do one. What is this example for? Here we'll just take his premises and then we'll prove it ourselves. Since he doesn't give us the paragraph that he's using, he must be referencing an earlier paragraph.
Yeah. Example B.
All right. So we have, as our premise, one, we have A implies B or C. Two,
B implies not A.
B implies not A.
And 3 is B implies not C. And 4 is A and D.
I won't bother doing the premise that depends on this premise anymore. Okay, so 5. So let's see, we're gonna do a reductio ad absurdum proof, except I don't know what we're trying to prove.
Probably A and D.
A implies not.
To illustrate this, give a particular example of an indirect proof. We reproved the validity of the conclusion of example 3. Not that. Okay. Let's just look at the conclusion real quick. A implies not D is what we're after. Oh, you said that? Sorry. A implies not D
Sorry.
is what we're after.
If you would have read like 2 more words.
Huh?
That's what we're proving.
Yeah, this is what we're trying to prove. These are our premises. So, assume by way of contradiction that this isn't true.
Okay.
Okay?
No.
Your premises, all your
Just
premises.
let him go. again.
I'm going to show that this being false is impossible, therefore it's true.
Okay, yeah, right. Okay.
So I'm going to introduce as a premise, I'm not sure how he's going to mark this premise, but I'm going to introduce as a premise, let's see how we want this to be. So if I'm doing, let me rewrite this. So A implies not D is the same thing as not A or not D is the same thing as not A and D, right?
Yeah.
Why are you rewriting it that way?
Because A and D right there.
Oh, that is the proof. Is that your point?
Oh my goodness, is that literally it? So if I introduce as another premise,
You already know that's impossible. You don't even need 1, 2,
Oh.
3.
You have to use 1, 2, 3, and 4.
No, that's.
this is a contradiction of this. We're misunderstanding something that he's doing. This is where he's saying, by way of contradiction, let this. Okay.
Oh, okay.
So these are my initial premises up here.
Oh.
This is my assume by way of contradiction this. Okay. So these are premises and this is
Conditional premise.
A and D
So we're assuming this.
by way of contradiction.
So we're assuming A and D is true, and we're going to show that.
And we're
it's
trying to get to
impossible.
this. Yeah, we're going to show that this leads to an impossible worldview.
So you're showing A and, or not A and B, basically.
So 5.
Right.
So since we know A and D, we know A. Tautologically implied by 4, we're now using premise 4. Right?
Yeah.
6, if we know A, we know
C is
not B.
true.
No, you know B
We
or
know
C.
B or C.
Oh, let me start with the D actually. So
Yeah.
I think I'm going to use D
And that
to
is-
get not
yeah.
C, and then use
B,
A.
so you know it's not A, and then not A and
Not
D
B.
is false.
Okay.
Which is impossible.
So A and D, we'll start with D.
And you're using 3 now.
Well, that's still just 4,
Oh,
but
yeah.
down here, now we're going to say not C, right? This is tautologically implied by 4 and 3, and now those are what we're using. Oops, not 4 and 3.
Yeah.
Yes.
Yeah, 4 and 3.
Tautologically
No.
implied by 5,
5 and 3.
and now we're using 3 and 4 as our premises. Okay, 7. So we have our not C.
Not
Now
C
you're using-
makes B.
Now we know that A is true.
Because of
That's
4.
tautologically implied by 4, so
Oh,
we're
right.
only using premise 4 here.
So now we know that B and C have to be true.
8.
B or C.
B or C.
Now I know
That's
that
4.
B or C has to be true.
And you know B's
And-
false.
No, you know C is
That-
false.
Oh wait,
Yeah, no, C.
I know A's true, which means I know B's false.
Right.
That's what I'm gonna say.
That's
I'm gonna say
first.
it's not B is tautologically implied by 7 and 2, and now we're using 2 and 4, right? So now I know
It's not B, then C.
let's see. So since I know not B, I'm gonna have to use an A again to say B or C, right?
Yeah.
So
B or C,
then
you know not B
I
and C.
know B or C. That's tautologically implied by. Let's see. We were using 7 and
1.
1. So this is using 1 and 4.
Oh, we know that's true because A is true.
Yeah. So from 7 and 1, I know B or C.
Right.
And now I know
B and
Not
C
B.
and
I know
not
B.
C.
B
So
is
C.
false and C is false.
Yeah, there you go.
From
So got a
B-
contradiction
false.
right there.
and not B, I know C, right?
What?
No,
you-
C is
you already
false.
used- C is
Yes.
false.
Look at line 6.
Look at that.
Oh.
Your contradictions
So
are.
you want to use these to say B. That's fine too. See?
What?
There's There's tons of different contradictions you can come up with. So you're saying we're using this line and this line to conclude B, right?
Yes.
I thought that's what you're saying.
Yes, you're concluding B and then you're showing not
Oh,
B.
yeah.
So
B,
Yeah. We
and that's
changed it
tautologically
as a
implied
bench.
by 6 and 9. So 6 uses 3 and 4, so we've used 1, 3, and 4. That's weird.
There's so many ways. Oh yeah.
Did we not use, oh, we're going to use 8 right now. So finally, 11, we have B and not B. That's tautologically implied by 10 and 8. And now we're using all our premises 1, 2, 3, 4.
We could, you also knew,
That is a contradiction.
And that's a contradiction, so 12, we know
Not
Not.
A,
A and B,
yeah, which is.
Wow.
which is deductio ad absurdum.
Wait, why do you know that?
Starting from line
Just prove
4
that A and B cannot be
to
possible.
line 10,
So that means
or
not
11.
A and B.
and now we're only using premises 1, 2, and 3. Now, 13, we have, yeah, we did this a longer way than we need to. That's the same thing as A implies not D. It's tautologically implied by line 12, and we're only using premises 1, 2, and 3. Right?
Okay, so real quick, take me back to line 11. Because we found a world where this cannot exist.
What did we find? We found A and D implies a contradiction.
Right.
So A and D can't be true.
So not.
So A and D is false, or not A and D is true.
Right.
And not A and D is just another way of writing this thing.
That was cool.
Good? Proof by contradiction. Okay.
This is as long as ours.
Huh?
Said his is as long as ours.
No, we
It's short,
couldn't,
actually.
because we took 2 lines that we didn't need. We didn't need these.
But he has.
there were 2
lots
different
of-
ways we could have gone, and we did both of them. and
Oh no, we did use not C. Anyways, doesn't matter. Our proof's perfectly fine. Okay. So I don't know if we went over the rule in its words verbatim, but the RAA rule. If contradiction is derived from P and not S, then S is derivable from P itself.
We will
So
get
that's-
the truth table, that's what.
Yeah, I think we skipped straight to the truth table and never actually said it in words. So that's what it is in words. And he has it right there. And so, what time is it?
Nice.
9:12. So that's it. So we'll just do examples and then we'll be done. So who wants to do this example?
Contradiction is derived from the premises and the negation of the formula S. Then S is derived from set.
Wait, which one are you doing?
The example, example 5.
Oh.
You ready to practice teaching, Jake?
Yeah, I'll read it to me.
Leah will read it to you. I'm gonna sit down.
off to a good start.
All right, class. Let me wake up on this day.
Okay, if 25 divisions are enough, then the general will win the battle.
D implies W.
Hey. How do you hear?
You're right, it's really big.
Okay. Either 3 wings of tactical air support will be provided, or the general will not win the battle.
A or not D.
Huh?
Don't do that
A or
with
not
W.
W.
Air support
Air support or
not
not
win.
win.
Sleep. That's true.
Also, it is not the case that 25 divisions are enough, so not D. And that 3 wings of tactical air support will be provided.
What's
So-
air support? A.
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 Yeah.
Were those all one sentence?
Yeah, it was all one sentence.
Read the sentence again.
Also, it is not the case that 25 divisions are enough and that 3 weeks of tactical air support will be provided.
Oh, so that's not D and A.
Yeah.
Therefore, 25 divisions are not enough.
Wait. So is it not
Therefore
D
not.
and A, or is it not D and A?
I thought it was not DNA.
Yeah, that's what it is. It's not-
Also, it is not the case that
it's not
25
the case that-
divisions are enough and that 3.
So it needs to be
Well,
not
it's
D
fine.
parentheses and
Just look at his real quick.
Yeah, not D.
A. No, it's not.
Not parentheses
Not D.
DNA. Something.
You don't
DNA.
include the D.
No.
That's all I do.
See if you can figure it out from there. Where does it go?
Oh.
Not DNA.
DNA.
Let me read that.
EW.
And then what was the last premise?
No, that's the
Therefore,
proof.
25 divisions are not enough.
So not D is what you're trying to prove.
Wow. You know that A is not true.
Yeah, A is not true, and W is not true. Which means,
D is not
No, aren't you supposed to
Well, you can
do in
start
your
out by
contradictions?
contradictions, so start
So
Yeah.
by
is it
D.
4? Isn't this going to be D? Assume D is true.
Yeah,
By way of
But-
contradiction, you gotta do.
but that's conditional premise. It's gonna come and go. So indent it, and then mark it however you want. So those other ones are premises. Okay.
Okay, then what do I need to do here again? Oh, I don't need to do those yet.
So you need to show that D being true along with those implies a contradiction. Some contradiction, any contradiction.
So if D is true, A is true.
How do you know that?
you know W. If D is true, you know W.
Yeah, D is true.
So W, 1. What do you do right here again?
It's tautologically implied T, comma, what lines you're using.
1,
And 4.
And now to the side in the set, keep track of the set of premises you've used.
1.
And 4. Because when it's all said and done, you can't still be using that 4.
Right. Okay, 6. So if W is true, then what?
A is false.
A is false.
Is the A is
1.
true?
4.
No, because we
No.
said W is true, so A is false.
1, 2, 4. Right? Oh, no, these are your
No, A
blanks.
is true. I think
A
she's
is
right.
true.
A is true.
Because if W is true, then
A or not
is
W
false.
is true.
Oh, that's not and.
Not W, yeah.
So A is true.
A is true, she's right.
And we use that. So this one you do lines. So lines 2 and
5.
5. And you use
Proved by
1, 2,
1, 2, 4.
Okay.
If A is true,
That is your contradiction.
oh, A and D being true.
You get not A from line 3. Line 3 says not A, and then your contradiction is A and not A.
Well, you get
what?
A and D, and you have a contradiction. Not A and D.
Distribute the not.
Right. That's what I'm saying.
But
That's
you,
what we're all
you
saying.
change it to an or, don't you?
Not D or not A.
Yeah, not D or not A.
Which is the same thing as not A.
No, it's
For these, yeah, but for
Why
these
do you
purposes,
change
for our
it?
purposes, it's what we need.
Okay, so you know,
So that's tautologically implied by 3,
Oh, yeah.
and that's not using premise 3.
Well, they're the exact same thing.
And that's all it's using.
okay,
And so you have A,
you
not A.
know D and A.
Not
are
yet.
true.
You need to use 4 and 7
Oh, because
to
you have
conclude
the,
not A.
yeah. Sleeping steps.
So since D is true,
Then not.
Then not A.
Look,
is
7
not-
says D or A is false.
right?
You know D is true, so A is,
false.
or not A is.
Sure.
So
Not A.
Therefore,
from tautological 5 from line 4, and that is just 4.
4 and 7.
Alright, yeah.
Yeah, you should be using all your premises now.
Now just was 7 more than
no,
3?
you have to use everything that you use from 7.
Let's see, you used line, so to conclude this,
The next
oh
step,
sorry, to conclude not A, what were you using?
Just this.
the next
Or-
step uses
Oh,
all.
right, I'm looking ahead. Yeah, the next step uses all. That's right.
No, you have to add 1 there. 4, 3, 1.
Okay, that's
No,
what
he
I'm wondering.
No, he doesn't.
He's not using one.
He's using line 5?
No,
He's using
4
4 and 7.
Line 4 and 7, my bad.
Yeah, you're good.
So now I have not A and A without
Yeah.
using line 4, right?
No, you use line 4, which is fine.
Because you're still in your contradiction.
So now you got A and not A. That's tautologically implied by 6 and 8.
Which is contradiction.
1, 2, 3, 4.
Mm-hmm. And that's contradiction.
They're supposed to.
But we use 4.
Right, you have to use 4 to do your proof by contradiction.
Okay.
You assumed not what you were after
You
and got a
assumed-
contradiction.
So now it has to be
Right?
right.
So now you can add it without the indent. So line 10, you can now conclude not D.
Right.
And that's using rule RAA from line 4 to line 9. And now you're only using premises 1, 2, and 3. Perfect.
You said I was writing today.
You did right. You made it number 1.
Okay. That was the end of the chapter.
End of chapter 2.
Yep. So we'll start chapter 3 next time. We can look at the homework real quick if any of those look interesting to you.
It's
Those are
just
interesting
one.
when I try and do 'em.
You have one and then you go A clear down to F.
Or if any of the previous ones you want to do,
There's
look
one,
at this
two,
previous
three, or four.
section for 2.3.
Wow, this guy kind of uses some of the techniques that
Biggest thing out then.
just
If you have 60% win rate. That's on $1.
Alright, so you don't want to do any exercises?
Let's do home.
Okay, then